So in the remaining 15-20 minutes I'll probably discuss some problems. So I'll do, I have here, yeah, maybe I'll start with this simple question. Yeah, so let's say I have this. So my question is to find V out of 0 plus and V out of infinity. So can you tell me how will I find if what is V out of 0 plus? Yeah, how do you say it's 0? Again, if the capacitor voltage has to change instantly, what should happen? An impulsive current has to flow. Now the impulsive current has to flow through this, so it has to come from the OTA. Now what is the current flowing out of the OTA? Gm times delta V of t minus, let us say, the output voltage. None of them is impulsive voltage, so the current is not impulsive. So V out of 0 plus is, how much is V out of 0 plus? 0. So then how much is V out of infinity? Delta V, is it? Why? Sorry? After a long time? But why is it fully charged to delta V? I mean, in steady state, what is one comment you can make about the capacitor current? What current is 0? Is capacitor current exactly 0 or some part of the capacitor current 0? Can I always say IC of t is 0 or something else of IC is 0? The DC part of the capacitor current is 0. So basically the average current is 0. So again here we are looking at the DC quantity. So average current through the capacitor is 0. Right. So this current is 0. So can you tell me what is this current in terms of the rest of the currents here at this node? I mean, at this node I have current flowing in this direction. That current is 0. What are the other currents I have? What is the current flowing down? V out by R out. So what is the other current I can have? I can have current flowing this way. How much is that? What is the current flowing this way? Minus Gm of delta V. Sum of these two must be equal to. So now what do you think V out is? Can V out be equal to delta V? That will not satisfy the equation. So you can work out from this and find out what is it. See, V out is exactly delta V when R out is infinity, right? So R out is infinity, then this term is not there, then this is 2. Right? So please don't directly jump to conclusions. Argue logically and verify. So maybe I'll not do the rest of the parts. So I think say third part I'll let you do it. Okay, maybe this one, let's see. What is the looking in resistance here approximately, do you think? Yeah, why 1 by Gm? Because drain? I'm getting word by word. Huh? Okay, he told drain. What is the next word? We are playing some. Okay, so let's say we apply test voltage, V test. So then so what is this is test voltage, so what is the current drawn by this fellow? Gm of which transistor times what is the current here if this voltage is V test? Minus or plus? Plus, minus. Why minus? The current from drain to source is Gm VGS, right? So this is going to be Gm 7 times. So again, now this current can flow through the R0 of the transistor, blah blah blah. But if you assume R0 is really large, these two currents must be same, roughly. So what is my R equivalent then? Roughly 1 by Gm 7. So yeah. Uh-huh.
In the previous lecture, you told that there is a if you assume that M5 to be resistance,
Yeah.
then the resistance, the equivalent resistance comes out to R1 plus R0 upon 1 plus GM R0.
No, okay.
So let's assume that
No. Okay, you cannot replace this with a resistor.
when we look from that below direction, it has
No. See, there is a difference, right? See, only if it's a one port network, you can do it. If I do something like this, then this becomes a one port network. This is equivalent to a single resistor for small signals, right? Whereas here that is not the case. See, what you are saying is probably what you are saying is this. So if I have this, you are saying looking in resistance is something, right? You calculate some RD plus R0 by 1 plus GM R0. Yeah, but that doesn't mean that this becomes equivalent to a single resistor of that value, right? See, again, remember the last class only we saw, if let us say I have something like this. So this is, let us say, some Rx. So what is the looking in resistance here, including Rx and R0? Rx plus R0 by 1 plus GM R0. So if you were to model this, this is as though I have a resistor. If I call this node A, from node A to ground I have a resistor of that particular value. That's what when I say that this is the equivalent resistance. So you can replace this, sorry, if you have something like this, then you can replace this with this. So if this is node A, node B, this also will become node A, node B. Whereas here if I call this node A, this will be node B, this is node C. Now when I say the looking in resistance is so much, it is a resistance from this node to small signal ground. So this is between the node A and the small signal ground here. So okay, yeah, so let's look at this again. This is something we looked today also. The question is, if I do some connection like this, will this voltage get defined properly? Yes or no? Why not? No? Yeah, I mean, yeah, I mean the same thing, right? See, here your idea is to make sure that the current in the transistors are equal to I0 by 2. So which means, again, if you want to bias it with a constant current, two things should happen: sense the current, find the difference, feed it back. Here there is no feeding back happening for M5, so the drain voltage will not be defined properly. Same thing, I mean, this is what I asked here also. I have two current sources. If I put in series, it won't be set properly. Yeah.
But if we consider the resistance of them,
output resistance of them, right? Yeah, then it will be set.
I not their output resistance, so it will be set now.
Yeah, but even then, you will not know what is that exact. See, the idea is, even in the example we took today, right? If it's an ideal current source, yeah, I mean, if you consider resistances across them, yeah, then the voltage is known to you. You can find out at least, right? But in a real case like this, it is not possible for you to keep the two currents equal. No, I mean, you have two current sources. What you are saying is, I have bias voltage 2, bias voltage 1. I can never try to make sure that the two currents are equal without, with very high probability, one of the transistors will go out of saturation. So there is probably a very small possibility with which this voltage will be sufficiently fine so that the transistors are in saturation. Yeah, I think that is about this. Okay, so let's do this. So let's do this part here. So this is your telescopic cascode, where I am doing low swing cascode instead of a high swing cascode connection like this. That's the difference. So D part is asking to find the minimum value of VB4 so that all transistors are in saturation. So let's try to do that. So how will you find what is the minimum VB4? Okay, that's the first thing. So I try to decrease VB4. First you figure out which transistor can go out of saturation. If I decrease VB4, what will happen first? So what can you say about the currents in the transistor? That is fixed. So which means the VGS of the transistor is, so which means if I reduce VB4, what will reduce first? Source voltage of this transistor will reduce. So which means which will go out of saturation now, right? So now what is the minimum VB4 I can have? I mean, remember what is the minimum that this voltage can drop to? If I call it VD2, what is the minimum of VD2? Okay, again remember that is all assuming, let us say I give you a fixed VB voltage. Then what is the minimum the drain can drop to? The minimum the drain can drop is one threshold below the gate, right? I have not given any information about VB. Right? If VB is not connected to an appropriate voltage, this cannot drop as low as 2 overdrive voltage. Remember, the fundamental battle is between drain and gate, right? So the minimum VD2 is how much? One threshold below. So I know the minimum of VD2. What is minimum of VB4? In terms of VD2, what is this voltage? VD2 plus VGS of which transistor? At whatever current you have, right? Something. So this is going to be your VB minus VTH2 plus VGS4. Okay, so then this is something I want you to work out. Yeah, so what is the output resistance here? What configuration this reminds you of? I mean, let us say I don't have this amplifier. What does it remind you of? So let me redraw this. Yeah, I am looking here. What configuration reminds you of? Folded cascode. So now I add an extra amplifier here. So what is this amplifier doing? It's gain boosting it. So for a normal cascode, what is the output resistance? Let us say this is M2, M1. Tell me R out. So if I call this as R out is GM2 times. This is approximately this value. Now we are not just having this normal folded cascode. I am putting this amplifier here. So how will the output resistance change? This gets multiplied by 1 plus A. This is straightforward extension. So here, I mean, what configuration is this in now? I look here. Same folded cascode, but what is this doing? This is same as what we saw here, just that this blue part is realized using the folded cascode. So here tell me what is the gain here. Gain is basically from this terminal. So this is going to be my input, this is going to be the output, I and O. Correct? So the gain is acting from this to this. So what is the gain if I call it, say, M3, M4? What is the gain of the gain boosting here? GM of which transistor? 4. Why? 3. There are only 3. I mean, how do you, okay. Okay, he is not even including any subscript. GM times R out, correct, yeah. Yeah, what is the GM? GM is coming from which transistor here? Input is fed to which transistor? So GM is coming from? So what is R out? R out is a resistance looking here. How much is that? R out 4 times. So, and you already computed the output resistance. So this A is what you computed now. Yeah, so here the same thing, extension. If I apply delta V in here, I am taking the output here. So once again, first recognize this circuit first. So first of all, this alone, how does it look like? Looks like a folded cascode. So what is this doing then? It's gain boosting. So again, GM times R out, short circuit GM and R out. So short circuit GM will be from which transistor? Input is applied to which transistor here? I mean, I'm looking at V out by V in, right, or delta V out by delta V in, right? Yeah. So V in is applied here. Which transistor will contribute to GM? M1 or M2? M1. So GM is from GM1. And how much is R out? So R out is the resistance looking here. So I am looking into the drain of the transistor and I have another current source here. So without the gain boosting, what is the output resistance? GM to RO2 times. Is that part clear? If I don't have this, it's a normal cascode. So now we have an additional gain. So let's find out what is that gain A. So how much is that? GM of which transistor? GM3 times. Again, remember the gain is we are having an amplifier from this as the input to this as the output. So the input is fed to M3, GM is from M3. The output is this terminal, so I look down. What do I have? GM4, RO4 times. Yeah, okay, fine. Yeah, correct. I am assuming this is gain is large, so that technically it's 1 plus A, but let's assume A is really large, so we can do this. Okay, so this again gain boosting. So here the question is, what is the minimum voltage VD2 can drop to? So what is the minimum voltage for VD2? What is the minimum this drain voltage can go here? 1 overdrive voltage of why? VGS of? And remember, if this voltage drops as low as 1 overdrive voltage, will this transistor be in saturation? Right, because that needs to have some particular VGS. So the minimum will be limited by MA or M2. M? Is that clear? I mean you assume that ideally you want this to go as low as 1 overdrive voltage. Again, let's take some numbers, about 50 millivolt or something. Not 50 millivolt, this guy will never turn on. So what is the minimum this can take here? VGS of MA at what current? Yeah, I think that's I know. In fact, this was the reason why in the gain boosting we did use an NMOS transistor here. We used a PMOS transistor here and then did a folded cascode there. Right? Okay. So I will not do this. Yeah, okay, let's just do this alone. How much is this? Yeah, why? Huh? Okay, I am trying to find Rn, so let's do step by step. What do you do first? Okay, you apply test voltage, and then I need to find the current here. So where will this current flow to? Can it flow here? So I just need to find this current. I need to find the current flowing into the OTA. To find the current flowing into the OTA, what should I find? Which voltage I have to find? The inverting terminal voltage here. So let's call this some Vx. So I am applying a test voltage at the gate, right? I am saying the output resistance of all transistors can be ignored here. So if the output resistance is ignored for small signals, how will this behave? Like open circuit. So if this is open circuit for small signals, what can you say about the small signal current? Small signal current is 0. Is it clear? I mean, for small signals this is going to be open circuit, so which means no current flows here. What is the small signal current produced by the transistor? Yeah, I mean it is 0, but in terms of whatever voltage is, Gm of which transistor times Vt minus, so this is 0. So what is Vx? Is it surprising that you apply Vtest here and I get Vtest here? Is it surprising? Why is it surprising? Yeah, it is common drain. So you are doing a source follower, we apply something at the gate, the same thing approximately comes at the source, right? So this voltage is basically Vtest. So what is this current? I mean, current in this direction is how much? Minus or plus? This is going to be plus Gm times. So what is the resistance now? Yeah. That's fine. See, if it's not trivial to start looking at infinite quantities, easier thing is to assume that finite R0 is there, and then at the end tend R0 to infinity. That's a common way of dealing with infinite quantities. Okay, so let me just do a couple of more. So this I'll leave. So here pole zeros, let me just do okay, I'll actually go to this problem set. Anyways, poles and zeros are here also. So here particularly what did I have here? Yeah, so let's look at this part, maybe common gate. So let's assume that RS is 0 in the first part, so this is short circuit, correct? So how many poles will be here now? This is the circuit, RS is 0, so how many poles will be there? 1 or 2? Why 2? Well, I mean, for finding the pole locations, what do you do for the input? You ground it. If I ground the input, what happens to the capacitor? It's gone. So how many poles are there? And what will be the location of the pole here? Yeah, what is the output resistance? I asked to ignore the R0 of this transistor. So the output resistance is how much? This is R2. Pole is 1 by R2 times. So in the second case, I asked you to consider RS, right? So, sorry. Yeah, but I asked to ignore R0 of the transistor. So let's say look at the poles first. So I make the input 0. Now how many poles are there? 2 poles. I can define both capacitor voltages independently. And here also I let's first ignore the R0 of the transistor. Right. So I have 2 poles. When can I write the pole as 1 by RC? Okay, let's check if it's coupled or uncoupled. So let's look at the resistance, seen by CL. Right? Do you think the resistance? I mean, I ignored the R0 of the transistor. So which means what is the resistance looking down here? Let me draw the same. I'm interested in the resistance looking down. R0 is infinity. How much will that be? I mean, what configuration this reminds you of? Cascode? If R0 is infinity, what is the output resistance? What is the cascode output resistance? Again, if R0 being infinity is a problem, assume finite R0. So what is the resistance now? Gm R0 times Rs roughly. R0 is infinity, this tends to. Now this is when C1 is open. So I short C1. What can you say about the output resistance now? If I short this with finite R0, what is the looking down resistance? This R0 of the transistor. Once again, if you ignore R0, this. So looking down, the resistance doesn't change. So looking up, it is R2. So CL is coupled to C1 or uncoupled to C1? Uncoupled. So now we can directly write the pole as 1 by R times C. Now if I know CL is uncoupled from C1, C1 is also uncoupled from CL. So let's do that. So I am looking, this is Rs. I am finding the resistance looking here, correct? Remember, I have ignored the R0 of the transistor. What is the resistance looking down here? Looking down is Rs. What is the resistance looking up? 1 by Gm, because R0 is assumed to be infinity. No need to worry. Okay. So now even if I go and short CL, the resistance looking up is still 1 by Gm. So you can write the pole location. So similarly, you can work out the other cases. Yeah, let me show you this. Okay, so let's take this case. So from our understanding, how many poles will the circuit have? Again, I'll make the input to be 0. How many capacitors I have? How many capacitor voltages I can define independently here? I can define both of them, no worries. So how many poles I should have? 2 poles. And how many zeros I might have? For zeros, I'll show this is the input. How many zeros I can have here? Because I can short any of the capacitor and the output is still non-zero. But once again, you can reduce this to a single capacitance, right? I can redraw the circuit like this. So this is my C1 in series with C2. So now how many poles and zeros I have here? 1 pole, there is no zero. So what happened to the other pole and zero? They get cancelled, right? That's unobservable or uncontrollable state. So what is this? Yeah, okay. So let's look at this. So first let's find the poles and zeros here. So for finding the pole location, what can I do to the input? Input will be made 0. So what will happen to the current source? So now how many poles I'll have? I have 1 capacitor, I can set the voltage across this. So I just need to find the equivalent resistance across the capacitance. So what is the equivalent resistance seen across the capacitance? So how will you find it? The capacitance was connected here. I need to find the equivalent resistance. So what do you do? Voltage, correct? And you find the this one. So what is the gate to source voltage here? So what can you say about the current? Let's ignore R0 for simplicity. So where will this current flow now? The only path for this current is to flow like this. So what is the test current? What is the test current here? So what is the equivalent resistance seen by C1? So the pole is at then. So for 0 you need to know the location of the input. So let's say I give this. So how will you find the location of the 0 now? Or first of all, is there a 0 here? If I short C1, is the output 0 or non-zero? I mean, if I short this one, the current is going to flow through RS. The output is still non-zero. So how will you find the location of 0 now? Yeah, let's assume V out to be 0. And then, okay, and then we'll apply KCL. So my input current is equal to this current plus this current. So if I call this some Vg, so what will be the current through the transistor? This direction, then Vg. What is the current this way? Minus Vg times SC1, right? So you work out, you'll find the 0 will be at, I think, 1 by Rs times 0. Okay, so since you are running really short of time, I'll directly write like this. So if you sketch the Bode plot of this, so I'll have at low frequencies I have something, and then I have a pole under 0. If I assume that my Gm times Rs is much greater than 1, will I first get the pole or the 0? 0 is going to come first. So which means after I encounter the 0, what will happen? And then what will happen? I'll encounter the pole. So what kind of circuit element behaves this way? It's an inductor. So if you have to model this impedance at low frequencies, I have a resistor. I mean, impedance is constant at low frequencies like this. That is a resistor. So at some frequencies it is actually increasing, so you need to have an inductor. Similarly, at very high frequencies the impedance is constant. That is once again a resistor. So you have to use, combination of these appropriately to model this behavior. Right? So you might have something like this, maybe, I don't know, something like this. Right? So at DC the inductor is short, so which means you have an effective resistance. Right? So let's assume that this resistor is large, this is small. So for DC, you have R large parallel R small, dominated by the small resistance here. As frequency slightly increases, R large is going to be really large, so that is not coming in picture. But now the inductor will start to dominate. It will do. Now at high frequencies, inductor is open, so which means now your R large will come. So in fact, this is one way to mimic an inductor using a capacitor and a transistor. You see that in this range of frequencies, you actually get an inductive behavior. Whereas if you flip the location of pole and 0, that is, if I assume GMRS to be less than 1, you might get something like this. You will first have this, you will get the pole first and the 0. Okay. So I'll stop here. I think a lot of time I spent.